Quick recap. So we talked about position and displacement. Position is where you are. Displacement is a change in where you are, a overall change in position. Its sign tells you which way you went. So if we're just dealing with 1D motion, whether you went east or west or right or left, whatever you want to call it, or up or down, or if overall you did not go anywhere. So you could run miles and miles and miles, but if you ended up back at your house, you did a round trip, your displacement is still zero. We then talked about average velocity and average speed. So average velocity is displacement over time. It's your average rate of change of position. Average speed is your distance traveled over time. So my best kind of way to distinguish the two is like a road trip. So this would actually be a 2D motion if you're thinking of an overhead view of you in your car. But you've got to get from point A to point B. Maybe it's one city to another. And the roadway, the highway, is some windy kind of road. Maybe that road is 300 miles. You're just all on highway for a very long time. So the distance, if we measure along that road, is 300 miles. And so if, well, let's say one more thing. Um, if you go directly from A to B, so sometimes you'll hear that said as the crow flies, a direct path from A to B. Maybe that's more like only 100 miles. Okay, if your trip takes 5 hours, what is your average velocity and what is your average speed? And let's say um, A to B is like southeast, just directly southeast. So start with average speed. What is average speed?
Total different distance over time.
Yeah, so which of those is the total distance you traveled? 300 or 100 miles?
Total distance would be 300.
Yeah, so your average speed is total distance, 300 miles over 5 hours. That would be 60 miles per hour. Okay. What about your average velocity?
That would be the 100 miles then.
Yeah. Is that just by process of elimination, or do you see why it is 100 miles per that 5 hours?
Assume you're taking the average of the distance, which is your displacement.
So,
Is it because it's that's our total displacement?
yeah, so it is total displacement. I wouldn't necessarily say displacement is the average distance, but it is how far if you took a direct path. It's the shortest distance. That's the magnitude of your displacement, at least. So, 100 miles over 5 hours, that's 20 miles per hour. And we do technically need a direction to fully specify, so that's where I'm saying the southeast bit. So that is the difference between the two. Your average speed takes into account the actual path you took. Your average velocity does not, but it does account for the overall direction you went, whereas average speed does not account for that direction. This is a pretty big difference for averages. We'll see when we think about instantaneous, what's happening right now, that difference kind of goes away because we shrink this down to a very tiny segment of the path. But we'll see that in a bit. Okay. This is what I want you to think of when you're trying to differentiate between the two things. All right. So we started on this example where we had a biker just going different ways. We've got his position time graph here, and we're calculating his average velocity. So we found in the first case he was moving in the positive direction or east. In this second segment, he's not moving, he's sitting still. And now we're on to this third segment. And so we chose a couple points to calculate the average velocity from. That's the slope between those 2 points. And so I'm comparing these 2 points right here. So I need this displacement and this time interval. That's going to be, all right, what's my displacement?
800, 400,
So you said 800 minus 400?
or the other way.
Yeah. So that's the thing I wanted to point out is that we always want to go final minus initial. The later time is where we're at 400. So we do that one first. It feels kind of backwards, but it makes the signs of things work out. Okay, and that happened between 1400 and 1800 seconds. So that's going to come out to -1 meter per second. So our slope is negative. What's that say about how he's moving?
He's going backwards.
Yeah, so in this case, west. He's returning from wherever he came from. But is he doing it faster or slower than he got to where he is now?
He's doing it slower.
Slower, because the rate is 1 meter per second compared to 2 getting here. So, and that's not to say necessarily he travels the same distance back as forward. You'd have to do integration, which we'll get to a little bit later to figure that out. But we can at least say he is heading back in the other direction on average. And so he's heading back the other way. And so we can always say that the average velocity has the same direction as the displacement, where something is moving overall. And that just comes from the fact that the numerator is the displacement, and that's the only thing that has a direction in this ratio. Okay, so now we move into, I want a better description of what's happening right now, because if I'm on that road trip, maybe my average speed is 60 miles per hour, but that doesn't mean I'm always going 60 miles per hour. Maybe my average velocity is 20 miles per hour, but that doesn't mean, for one, I'm always going 20 miles per hour. I'm definitely not. But two, that I'm always going directly southeast. So we want something that describes all of that a little better, with the sacrifice that the math gets a little bit trickier because you have to keep track of what's happening at every instant. So that's what we call instantaneous velocity for the one that cares about direction, and instantaneous speed for the one that does not. So instantaneous velocity, how fast and which way. An object is moving at an instant. So how fast you're going right now and which way you're going right now. Instantaneous speed, I'm going to skip that v equals for just a second, is just how fast an object's moving at an instant. It really is, in this case, directly related to the instantaneous velocity. It's just the size of it. For the velocity, we'll get like plus 2 meters per second at a certain instant or minus or whatever. If you just take away the sign of that, you're just left with the number. That is the instantaneous speed. So the magnitude of velocity. Okay, so where would you tend to see the instantaneous speed on that road trip? What's telling you that information?
A speedometer?
Yeah. So how it's doing that is actually calculating an average speed over very short distances. And that's going to approximate the instantaneous speed. So this is roughly what a speedometer is measuring. Okay, now back to that V equals part. So we don't want to throw out the tools we've already developed for talking about speed and velocity. So let's think of if we took an average velocity and did like they do with the speedometer. You think of just a very short time interval and a very short associated distance or displacement. In that case, you can approximate better and better how fast you're going right this instant. So if I think about, all right, so I come back to this road trip idea. What I'm thinking about now is not the whole trip, it's just a very short segment of it. So maybe from A to, we'll call it A2. In that case, hopefully you can see that my distance, whatever it is, and my displacement have pretty similar lengths to them. So displacement's the straight line, the direct path. Distance is actually traveling along that curve. As I shrink to shorter and shorter time intervals, though, those two tend to agree at a certain point. And that's what we're saying about instantaneous speed ends up being just the size of your instantaneous velocity. But we're just finding that instantaneous speed or velocity by considering shorter and shorter time intervals of our average value. So we think about the limiting case as we shrink the time interval to 0 of our average velocity. So what is that right there? Limit as the bottom thing goes to 0 of a ratio of two things.
Derivative.
Yeah. So instantaneous velocity is the derivative of position with respect to time. Rate of change of position right this instant. Okay. And so graphically, we can do the same thing. And it's a little bit easier to visualize what this means on a graph. So if something's velocity is changing, that means the slope on your position time graph is changing. And so you don't have a straight line anymore. You have a curve. That's what we're seeing down here. But we can apply this idea that we just came up with. So on the graph, what is that right there? Delta x over delta t. At the end of all of this, how fast I'm going right at 20 seconds. But I could start by saying, well, what is my average velocity from 20 to 25 seconds? What would that be on my graph?
It's the slope.
It's the slope, yeah. You might remember this as your secant line between 2 points. But I want to shrink that time interval, so my delta t, down to 0. And as I do that, that second point gets closer and closer to the first one, and my time interval gets smaller and smaller. So I'm calculating the slope between all these intermediate points until eventually my second point overlaps with the first, and I'm finding the slope right at my point of interest. So I'm finding the slope right at 20 seconds. Okay, and that's the visual or graphical interpretation of a derivative. It's the slope at a single point. And so that's the slope of the tangent line to the curve at the time we're interested in. Okay, so that green line right there, I'll extend it out just a little bit. That's our tangent line. Okay, and then to actually find that slope, right, we have our tools of calculus, different power rules and chain rule and all those, I don't know, maybe not fun things, all those things. So we're going to try that here. I want you to just start by calculating. Just refresh yourself on derivatives. Take a minute, try to find the velocity in each of these four cases as a function of time. So you've got position as a function of time. Find velocity. Start with the first one. What is the velocity as a function of time for the first one?
Simply 3.
Yep, just 3. So what's that telling you about that velocity? The fact that it's just the number 3.
Constant.
Yeah, it's never changing. And you can see that from the graph too. The slope is always the same value no matter which point you're looking at. So it looks just like the average velocity. And that is the case. If you have a constant velocity, the instantaneous equals the average velocity. So in this case, v is constant. And which direction are you moving? Say positive is east, negative is west.
Positive.
Yeah. So the slope's positive, and that's telling you that information. Constant and positive, or east if we were calling it east. Okay, move on to the next one. All right, so someone else, tell me about the velocity as a function of time for this one.
Negative 8t.
Yep. Okay. So what is that telling you is happening as time goes on? So as t gets larger and larger.
The slope is starting to go more negative with
Yeah,
every second.
exactly. And we can see that here too. As time goes on, my slope gets more and more negative. So velocity is becoming more negative. So they're moving in the negative direction. Are they speeding up or slowing down?
They're speeding up.
Yeah. So don't let the negative here confuse you. That's telling you about the direction that this thing is moving. It's not telling you necessarily that it's speeding up or slowing down. How we see that is how this slope itself is changing. So if slope's getting more and more negative, that just means they're going faster and faster in the negative direction. So they're actually speeding up. Okay, yet a third person. Tell me about the velocity in this case.
I said negative 1t.
Okay, so we've got 2 over t squared. Come out over here. That's 2t to the negative 2. When you take your derivative, how did you do that?
I didn't put it to 2t minus 2. I just switched the 2 in the t2, put a negative in front of the t2, and then took the derivative of that.
Okay, so it sounds like you maybe did something closer to like that, or t squared over 2 maybe?
Yeah, yeah.
Okay. So that would be the derivative of the reciprocal of this thing. So that's not quite it. Um, anyone else have an answer on that?
Negative four
Negative.
over
Negative
You can go.
4, what?
negative four
You can
over
go
two.
ahead.
Okay, I think I'm hearing it. Just fighting.
Negative 4 over t is the
Okay.
derivative.
All right, still not quite. Is t cubed. because you subtract one, right? So 2t to the negative 2, you bring down that negative 2, and then you subtract 1. So you go to negative 3. You're thinking more of the integral. So that'll be negative 4 over t cubed. Okay. So what's happening as time goes on for this one?
Gradual decrease in the positive direction until it levels out in a limit.
Okay. So I agree with everything except for in the positive direction. Is this thing moving in the positive direction? So V is negative at all times if we're talking about positive time, right? So they're always moving actually in the negative direction, but you're right that they are slowing down. That V is becoming smaller and smaller in the negative direction until at least asymptotically it's zero speed. So they're slowing down to zero after infinite time. Not really realistic, but that's what this graph is saying is happening. So our slope starts out pretty negative. It's a large negative value. But as you said, it levels out over time, gets flatter and flatter until eventually, meaning after infinite time, that slope is zero, meaning they come to a stop. So V is becoming less negative over time. They are slowing down. Okay, and last one. I saved you a nice one as a break from those middle two.
It's 0.
Yeah. So derivative of a constant is 0. And all that's saying is, what is the slope of a flat line? It's 0. There is no change in position in this case. This thing is always stationary. Okay, so we've seen what graphs can look like for something that's moving at a constant rate, speeding up, slowing down, and just sitting still. So these questions are real easy now. We've pretty much answered them. When is the velocity constant? Which two cases?
1 and 4.
Yep, 1 and 4. Because just looking at the graphs, we can see a constant velocity corresponds to a straight line on your position time graph. So in 1, they are actually moving. In 4, they're not, but both are considered constant velocities. Okay. When is V in the negative direction?
3.
The 3 and 2.
Yep. So what tells you that something has a negative velocity on your position time graph?
It has a negative sign.
What has a negative? So I
The
agree if you're talking,
velocity.
yeah, if you're talking about like our formula we got here, say I didn't give you that, I just gave you the graph. How would you be able to tell?
The slope goes down.
Yeah, that's all it is. Okay, and a positive velocity, of course, is that the slope goes upward. And you can see something that has a little bit of both over time. You can see something like that for your position time graph. At first, something's moving in the positive direction, then it stops, then it moves in the negative direction. Can you see that, or was that like, I have no idea how you got that? I'm guessing the latter, which is fine. If I look early on this, I see that my slope is positive. but it gets less and less and less positive until eventually it's flat. The slope is 0 at the top of this thing. I reach a maximum in position, meaning I turn around. And then my slope gets more and more and more negative. So I'm going back the other direction. That's all that graph is saying. So we can see combinations of motions. You can see pretty much anything on a position time graph, but now you know how to interpret that as far as how something's moving, whether it's moving forward or backward, or if it's come to a stop. Okay. So let's actually draw a velocity time graph based on our position time graph. So we're not given a function in this case to differentiate. We're asked to basically graphically differentiate. So I think the easiest place to start is always, where is the velocity 0? So where is it 0?
At 9 seconds and more.
Yep. So we can come over here. We know it's 0 meters per second here at the end because the slope right here is 0. Okay, anywhere else?
Is it 0 at 0?
Yeah, from about 0 to 1. So the slope is 0 there. That's telling us that our velocity is 0 in that interval. Okay, now it's easiest to move next to, where's the velocity constant? So how can we tell that we've got a constant velocity?
Slope doesn't change.
Yeah. And so we're dealing with a straight line, something where the slope is always the same value. That happens from, I'd say, about 3 to 8 seconds. So we're not necessarily given that value clearly enough. So I'll tell you, it's about 4 meters here and about 24 up here. Okay, so how can I find the value of that velocity from 3 to 8 seconds?
Use the slope formula?
Yeah, and that works because if you have a constant velocity, like we said, the instantaneous and average velocities are the same number, right? The slope at any point is the same as the slope between any 2 points if you're dealing with a straight line. So our slope would be what over what? So we need rise over run.
Is it
Plus,
24 minus 4 over 8 minus 3?
There you go. 24 minus 4, and then I could add my positives here, right? Be an extra about that so that we know we're dealing with positions and vector quantities, but I think we're okay at this point. All right, so we get that, and that comes out to positive 4 meters per second. So I will put that positive to emphasize we're moving in the positive direction during this bit. So I come back over to my velocity time graph. I'm realizing now that I'm moving at 4 meters per second in the positive direction from 3 to 8 seconds. I have a constant velocity of positive 4 meters per second. Okay, the other 2 times, so from 1 to 3 seconds and then from 8 to 9 seconds. Tell me, we don't necessarily know exactly how it behaves without a formula there. We can kind of guess at it. Just tell me about how the slope is changing. So from 1 to 3 seconds, how is that slope changing?
It's speeding up.
Yeah, so the slope is getting larger and larger. And so we can at least say from 1 to 3 seconds, my velocity is increasing. Now, I don't know necessarily that it's increasing at a constant rate, which would correspond to what's called a constant acceleration. But here I'm just kind of connecting the dots and saying, I'm going to linearly interpolate. Engineers love linear interpolation, except in thermodynamics. It sucks in that class. So in that range, your speed and your velocity is increasing. Okay, and last, tell me about what the slope is doing from 8 to 9 seconds.
It's flattening out to a constant rate, so it's going down.
Yeah, so getting less and less steep. Slope is decreasing. And what is that constant rate it's decreasing to?
26 meters.
Not the position, because that would be the position. What is the rate it's decreasing to? So the
0.
velocity, 0. There you go. So it's decreasing in this interval. And again, just from my graph over there, I don't necessarily know that it's decreasing at a constant rate, but I'm linearly interpolating. I'm connecting the dots because without sampling some points off my first graph and getting more intense with the estimating derivatives, that's all I got. Okay, so in that range, v, your velocity is decreasing. All right, so slope on position time graph is always velocity. That's what it's telling you about. And so if you can see what the slope's doing, you know what the velocity is doing for any time interval. Does this graph make sense for an elevator? Is this your experience with an elevator? Think of x as really a vertical coordinate. You're walking to the elevator, you get in. Okay, elevator is stationary at first, sounds good to me. Then it speeds up because it has to get moving until a little bit later, it levels out, right? You're moving at a steady pace. And you keep doing that until you get near the top where it slows down again. And up at the very top, you come to a stop at your floor and you exit. Looks about right to me. Okay, so you come in, you're stationary, then you speed up, then you move at a constant rate, then slow down, and then stop again. So this is reflecting something in reality to a decent approximation. This linear stuff we definitely wouldn't see on that. You have some other things that make the elevator ride a little bit smoother, so you don't get these very sudden changes in velocity, what you'd call an acceleration and then a change in acceleration or a jerk. But this is a good approximation of that. Okay, so let's talk more about acceleration. Now that we're used to velocity, acceleration is not too bad as far as the math goes. It's very similar. It's harder as far as the concept of acceleration because we all think we know what it is and we don't. So acceleration to us is pretty much only speeding up. That's not true in physics. It's any change in velocity whatsoever. Absolutely any change is an acceleration. So speeding up is the one we're used to. Slowing down, we hear it called in everyday life a deceleration, but is still considered an acceleration in physics. And this is the worst one of all, the one everyone forgets. Changing direction. Because any of these correspond to a change in your velocity, since velocity is telling you both about the rate, the first two things, and the direction of motion. So I'm going to triple underline this one so you don't forget it. This means that if you're in your car, you take a turn, but you're going at constant speed, your speedometer reading never changes during that turn, you're still accelerating because your direction is changing. Okay, so start with average, go to instantaneous, and you'll see that we kind of leave averages in the dust after really chapter 3. So instantaneous is the one you're gonna want to be remembering most. And that's why, for instance, on velocity, you see I put instantaneous in parentheses because eventually we just call it velocity. Okay. Average acceleration is an object's change in velocity over the time it takes. So final minus initial velocity over final minus initial time, or change in velocity over change in time. So that's final, that's initial velocities. Okay, what would the units of acceleration be?
Meters per second squared.
Yeah, and I'm gonna say it, this is my other thing I'm very neurotic about. I'm gonna do my best to always say meters per second. But we do abbreviate that because of that algebra of units as meters per second squared. But physically, what it's telling you is the number of change in meters per second. So 4 meters per second squared is saying, on average, your velocity is changing by 4 meters per second each second. All right, so an example of that, a plane accelerates, attaining a velocity of 260 kilometers per hour after 29 seconds. What is the plane's average acceleration? So its initial velocity is 0. All right. I didn't say that here, but it's accelerating down a runway. Hopefully it wasn't moving at first. And we need to calculate its average acceleration. So what would I put here? How would I calculate this?
Uh, 260 minus 0 over 29 minus 0.
Yep. So yeah, it wasn't stated that my initial time was 0, but if nothing's telling you otherwise, you can always assume that because in a sense, you're the one choosing where you start your stopwatch. That will come out to, if we just divide as is, 9. What are my units here if I leave it this way?
Meters per second per second.
Are they?
Kilometers an hour or kilometers a second?
See, so this is where it's a little confusing because we've got competing time units, hours and seconds. We can do this as long as we're clear what it means, and we'll clarify here in just a second on the picture. This would be 9 kilometers per hour per second. If we had converted that 29 seconds to hours or converted the kilometers per hour to kilometers per second, we would have more consistent units. For instance, kilometers per hour squared or kilometers per second squared. But we can use mixed units if we want, if we understand what they mean. So acceleration is positive 9 kilometers per hour per second. And it is an average, so I should add average there. Okay, this is saying that on average, my velocity is changing by 9 kilometers per hour each second. That doesn't necessarily mean that absolutely every single second it's changing by exactly that amount. But if that acceleration is constant, it does mean that. Okay, so if your average is actually what it is at every instant as well, then it does mean your velocity is changing by 9 kilometers per hour each second. If I assume that, I can say that after about 1 second, this plane is going 9 kilometers per hour. It gained 9 kilometers per hour per that 1 second. So how fast is it going after 2 seconds?
18.
Yep. So don't let the term constant acceleration confuse you. This is what it's saying, that your velocity is changing by the same amount each second. It just sounds almost like an oxymoron, constant acceleration. It just means the rate at which your velocity is changing is constant. Okay, we can also pull from this that if your initial velocity is positive, or at least not negative, and your acceleration is positive, the thing speeds up. So the plane here is speeding up. Speed increases. So that's a big takeaway from this as well. Okay, you take just a minute and try this one. We'll say take till. So what did we get for that average acceleration?
-5 meters per second.
Yep. So final minus initial velocity plus 13 meters per second minus plus 28. I'm not gonna like count you off if you don't put the pluses, or if you, I don't know, say you say meters per second squared or something. That's my own neuroticism. It doesn't get passed on to you other than I'll just like mention mine again if you say one of those. Um, okay, so that does come out to -5 meters per second, or if we abbreviate meters per second squared. Actually, I'm sorry, I do want to put meters per second first. I just think it helps because otherwise you end up halfway into the semester and then you have that identity crisis of what is a second squared? And you're right, it's nothing. It isn't a thing. It's just an abbreviation for meters per second per second. Um, okay. And so our acceleration is negative. It's a vector in the negative direction. Our initial velocity was positive 28 meters per second. So assuming this acceleration is constant, meaning it's not just on average how our velocity is changing each second, but it is exactly how much our velocity is changing at any instant. How fast is our drag racer going after 1 second?
13 meters per second.
That's after 3 seconds, right? Because that's from 9 to 12 seconds. So what about after just 1 second?
Is it 23 meters per second?
Yeah, that average acceleration, it shaves off 5 meters per second each second. So now velocity is a little bit less. And after 1 more second, how fast is it?
18 meters per second.
Yep. And after 1 more second, it will be that 13 meters per second final velocity. Okay, so what we observe from this is that if your initial velocity is positive and your acceleration is negative, speed decreases, slows down. Okay, so that's again telling you on average how your velocity is changing. It doesn't get so much usage. We usually do talk about the instantaneous acceleration, but you can always estimate it with an average acceleration. That's more the use of average in this case. So this is how quickly velocity changes at an instant. Oh, he is changing. So it gives you an idea of in the next instant, how will your velocity have changed? What will its new value be just a very, very short time later? Um, I sometimes hear acceleration described as how quickly, how fast changes. And I don't know if that's less or more confusing for one, but it also doesn't bake in that direction changing is an acceleration. So take that as you will. But this works just like with instantaneous velocity. You consider a limiting case of average acceleration as you think about shorter and shorter time intervals to take your average over. So this is the derivative of velocity with respect to time. Okay, so here is our velocity time graph from before, and we want to make an acceleration time graph. This works exactly how you think it does. You velocity time graph takes the role of your position time graph, acceleration time takes the role of your velocity time graph, meaning find slopes on the velocity time graph, and that will tell you your accelerations. So where's my acceleration 0?
From 3 to 8 seconds.
3 to 8 seconds. Yeah. So over this whole span, I see that my slope on my velocity time graph, so it is important that it's velocity time, not position time. My slope is 0. And so my acceleration is 0. All right, where else?
0 to 1 seconds.
Yeah, and go ahead and give me that other one too.
And 9 to
Whenever,
wherever.
yeah. All right, so slope is 0. So acceleration is 0. Slope is 0. So acceleration is 0. Okay. Now tell me about from 1 to 3 seconds. What can we say about my acceleration?
It goes up by 2.
Okay, so you're saying that the acceleration is 2?
No.
Okay. Explain it a little more to me.
Um, I don't know how to explain.
Okay, that's fine. So from 1 to 3 seconds, so that's a span of 2 seconds, my velocity increased by 4 meters per second. What does that tell you about my average acceleration at the very least? I increased by 4 meters per second per those 2 seconds. So I ended up at 4 meters per second from 0 over this 2 second span that was from 1 to 3 seconds on my graph. Right, that's plus 2. So what is that saying? It's saying that the elevator's speeding up during this bit, okay? Because it had initially 0 velocity and a positive acceleration is going to gain speed as it moves. So it's an acceleration of positive 2. And so the elevator is speeding up because my initial velocity was 0 and my acceleration or my initial velocity was at least not negative, and my acceleration is positive. In other words, they're in the same direction. That's the important piece here. It doesn't tell me anything about like at these kinks on my velocity time graph. So I just have to assume it's a discontinuous jump if there's no smoothing happening here. Really, a more realistic graph would have like a smoother profile there, and similar for here. But that would get us into dealing with a changing acceleration that's not just like piecewise constant. And then you're dealing with the rate of change of acceleration, which is called a jerk, but we're not going to ever touch on that in the class. Okay, and the average acceleration from 8 to 9 seconds. Could someone find that for me?
Would it be -4 between 8 and 9?
Um,
I mean, -4 meters per second squared.
yeah. Yeah, so our final value was 0 for our velocity. Our initial value was +4. I'm trying to match the angle of this thing here, but it's clearly not working out. So hopefully you can see what I'm writing here. And this was from 8 to 9 seconds. This does come out to -4 meters per second per second. And why? So I'm calculating average acceleration here, but on the right is my acceleration, meaning instantaneous acceleration time graph. So why can I just transfer this average acceleration over to that graph without changing anything? In other words, why can I call this average acceleration I just calculated my instantaneous acceleration as well?
Is it because it doesn't like fluctuate?
Yeah, so it's the same justification as why we can say an average velocity is equal to the instantaneous. It's that if your acceleration at every point, meaning the slope at every point, is the same, then you've just got a straight line. And so the average, the slope between two different points, is going to have that value as well. So on a position time graph, if you have a straight line, that means constant velocity, and so it equals the average velocity. If you have a straight line on velocity time graphs, that means your acceleration is constant, and so equal to the average acceleration. But this was -4, and again, we kind of have a discontinuous jump here. Okay, so what is happening in this bit? You're still moving in the positive direction because your velocity is still positive, but your acceleration is negative. So what is the elevator doing at this point?
Slowing down.
Yep. And we knew that already by looking at our velocity time graph. This is just yet another way of seeing it. And our justification is that the velocity and acceleration had opposite signs. Okay. Last thing I want to say here is, what would you feel if you were riding this elevator? So when you first get on it, nothing really special happens, right? You're just standing there. But when you start moving upward, do you feel a little different?
Yeah, it feels like it's pushing down on you.
Yeah, you feel a little bit squished into the floor. So I'm going to exaggerate that and say you're a little squished guy. Squished or squashed. But once things kind of settle out, you're moving at a constant velocity again. So your acceleration is 0. You're back to normal. You're good again. Okay, but now the elevator is slowing to a stop. During that slowing down bit, do you feel a little bit different as well?
Yeah, it's like negative G's. It feels like you're rising up.
Yeah, feel a little bit lightheaded. Or I do at least. But once the elevator comes to a stop, you're back to normal, at least physically. Probably, your body's still kind of reaching that equilibrium again, but you feel at least like you're on solid ground again. Okay, so we sense those accelerations and we feel regular when we don't have an acceleration happening. In other words, humans are living accelerometers. We are natural sensors of acceleration. So acceleration is going to be a very important quantity as far as not only how we move, but what we feel about motion. Yeah, this is just kind of really quickly summarizing at the bottom the stuff we've already said for velocity. Okay, so what have we learned about the relationship between acceleration and velocity? If you have acceleration and initial velocity in the same direction, what happens to something's speed?
It increases.
Yep. And if the directions are opposite, it decreases. That goes no matter what your pairing of directions are. So keep that in mind for this example. Something's moving along an x-axis. We don't know which way at this point. We're just asked what is the sign of its acceleration depending on these different motions. So if it's moving in the positive direction with increasing speed, what is the sign of its acceleration?
Positive.
Yep. So how did you decide that?
Since they're both going in the same direction, we know that's increasing, so the acceleration has to be a positive, I'm assuming.
Well, so that's kind of answering, assuming you knew the sign of the acceleration already, right? To say that they're in the same direction. So this is a slightly altered argument, but still concluding the same thing. Right? You're moving in the positive direction. I agree with that. But what you're given in this case is that the speed is increasing. But you can go in that direction as well and say, because of that, acceleration has the same sign as v. And so it must be positive as well. And I know that's what you're getting at. I'm just making sure that's clear to everyone else. Okay, positive direction with decreasing speed. What's the sign of our acceleration? So v is positive. What does this say about the sign of the acceleration compared to the sign of the velocity?
It's different.
It's different. And so it must be negative. Okay, those are the ones we've done already. Use that to guide these last two. You're moving in the negative direction with increasing speeds. You're just moving west is all this means. Nothing special about speeding up, slowing down in that negative direction piece. It's just saying you're moving west instead of east. So what is the sign of your acceleration here?
I'm going to say positive.
Is
I
it?
think it's actually negative, I believe.
Yeah, that's the tricky bit, right? Where acceleration, a speeding up, feels like it's got to have a positive associated with it. But the positives and negatives tell us about directions of things, not necessarily rates of things. So all this tells us, increasing speed, is that A must have the same sign as your velocity. And that sign is negative. So if you're moving in the negative direction, a negative acceleration is actually speeding you up. And last, in the negative direction, with decreasing speed is the other one, right? Positive. Because decreasing speed means acceleration has the opposite sign. I like to think of this kind of drag racer example in either case to think about like speeding up, slowing down. So the acceleration is the direction the parachute's pulling, the drag chute, right? So as long as the acceleration's opposite the direction you're going, that's what's going to make you slow down. It's hitting you in the face saying, no, go back the other way, meaning slow down. And so if you're moving in the negative direction, the direction that push on you would be to tell you to slow down is actually in the positive direction. If you're going in the negative direction and there's a push telling you to speed up, that push would also be in the negative direction. Hopefully that helps and I didn't just make it more confusing. Okay, so quick recap, displacement is where you're moving. It doesn't care about how you got there. It just cares that you were at point A, now you're at point B, how far is point B from point A, and in what direction. Velocity is how you're moving. Meaning with what speed and in what direction. And acceleration is how your motion is changing. And motion does, again, mean speed or direction. So if either is changing, you are accelerating. And I guess I didn't put vector hats in everything else. So these are, we'll add them in the next chapters. We don't really need them in 1D, but in 2D and higher, it becomes very important to distinguish between vectors and scalars. So we add a little arrow hat to talk about vectors. Okay. Any questions at this point? That's kind of a lot to absorb. And I know it feels like stuff that we all know, but I do think reading over this part is the most important, the acceleration bit, because it sticks with you the whole semester. And if it doesn't click, it really gums up the works for everything else. So don't take for granted that you know what acceleration is. Most people don't. I didn't when I took physics. So we kind of turn to this simpler case. I said we're not going to talk too much about a changing acceleration because that would constitute talking about a rate of change of acceleration, which is jerk. By the way, there's higher derivatives than that. So jerk would be third derivative of position with respect to time. Oh, I never said that up here, did I? So derivative of velocity with respect to time. That would then be, since, whoops, velocity is the derivative of position with respect to time. We could also write this as the second derivative of position with respect to time. But what I was saying about jerk, it's the third derivative, and then there's a fourth derivative that's snap. The fifth derivative is crackle. The sixth is pop, and then lock, and then drop. And I'm not making any of that up. All right, but we're going to mostly stick to constant acceleration. So remember this, it feels like a weird thing, constant acceleration, but it just means something's undergoing the same change in velocity each second. So the plane speeding up by 9 kilometers per hour each second, or the drag racer slowing down by 5 meters per second each second, those are constant accelerations. So we have talked about 5 things describing the motion of an object. That's displacement, delta x, or final minus initial position. Initial velocity. So that's the velocity at time t0, t initial. The book uses t1 and t2 instead of t0 and t, but then suddenly switches over to t0 and t in this section. So I just never bothered with t1 and t2. This is v0. The final velocity. So the velocity at your later time t, and that's v. Our acceleration, which again must be a constant value for the things we're about to say to apply. That's a. And then how much time has passed. So t minus your initial time. These are all the things you need to describe completely the motion of something that has a constant acceleration. So we're going to come up with these kinematic equations, and I'm going to do this real fast because all the algebra is already written out. And it's not super important. What is important is the final equations. We really could get by with just these two, but that is extra work on us because then we have to solve for anything that's not in those two every single time rather than taking the most convenient route. So that's what the kinematic equations do for us, is a convenient way of finding any quantity given the others. We'll always assume you have the stopwatch starting when the thing is at whatever the initial position is, what you're calling the initial position. We've said that if acceleration is constant, meaning the velocity time graph has a straight line on it, then the instantaneous and average acceleration are the same. So we can equate them and then rearrange. This is just me saying initial time is 0. If we rearrange, we get our first kinematic equation. So we'll bank that for later. We can do a similar thing for the average velocity. And so we get this kind of intermediate equation. We're going to combine that with another one. If we think about on our velocity time graph, something increasing in velocity from an initial value to a final value, right? There. Hopefully you can see that the average velocity is just halfway between those two extremes. So the velocity is increasing, but on average, it's about in the middle of those. So that's all this is saying. Just take the average of those two. That is your average velocity. If we combine that with this equation that we had up above, we get our second kinematic equation. Then we just kind of slap those two together in various ways to come up with our other two. So eliminating different things leads you to the remaining 3 kinematic equations. So we have 5. Why do we have 5? Because they let you find any one thing given the other 3 without knowing about a 5th. Okay. So if I want to find initial velocity and I know final, the time that's passed, and the displacement, I should use this second kinematic equation. And if I'm not given anything about acceleration. If I'm given other quantities, I pick a different one. So we'll see that in examples that we'll start on next time. So that's where we'll start in the next bit, is applying these in a couple of examples. All right. Whirlwind derivation, you can read through it in more detail if you want, but the end goal was just these 5 kinematic equations relating our kinematic variables, meaning the variables describing the motion of something. Okay, are there any questions before we sign off for today?
Are they really called snap, crackle, pop, drop, and lock?
Absolutely. You can look it up on Wikipedia. It is a real thing.
Just blows my mind.
Yeah. Yeah. And it's because, okay, anything past jerk, you pretty much almost never see. I've seen sometimes for like suspension systems that there may be something called like snap reduction, but it's just not as common of a, you don't usually go that far into the rates of change. You're usually content with like jerk at most. Oh, and roller coasters, that's where it'll show up sometimes too, is you don't want those to be too jerky, and so you get into how are all of those things changing up to like the 4th or 5th derivative. Well, then I will see you all on Tuesday, finally in person. I'm really looking forward to that because teaching on Zoom sucks. I know taking classes on Zoom sucks. So I will see you all then.
See you.
Alrighty, have a good day, everyone.